Okay, we're going to learn another way to approximate the solution to a different differential equation. Remember, a differential equation is just an equation that has a derivative in it. So in this problem, this is a differential equation. You got a derivative, you have an equation. So the idea with Slowfield's Euler's method that we're going to learn today is that even though we may not be able to solve the differential equation, we can still find out information about the original function. Now, I'm going to do a problem. This is actually a differential equation that we can solve, okay? Because I just want to show you the difference between the actual solutions and the approximations. Looking at a Slowfield, looking at Euler's method. So let's actually go through and solve this. So this one, if I solve it, right, this is really y equals x squared over 2 plus c. Notice I do give you a point to plug in. So if I plug in 0 for x, 1 for y, you do end up with c equals 1. So this would be the actual solution. Okay. Now, a Slowfield, remember, is a graphical representation of this differential equation. And remember what we learned is it's just like plotting points, right? So when x is 0, the slope, based on my differential equation, is always 0. So that means I have horizontal tangent lines here also. When x is 1, based on my differential equation here, dy dx is always the x value, which would be 1. So I'm going to draw a tangent line that has an approximate slope of 1. And then you can go ahead and continue the pattern. When x is 2, dy dx is whatever x is. So really for this one, pretty easy to create the Slowfield. And I could go ahead and do it for -1 and then do the same thing for -2. And you can see as I draw these Slowfields, and then you can see the parabolas being formed. And the one at 0, 1 is this one right here. This would be that particular graph. Okay, so your Slowfield is a graphical representation of the differential. Now, Euler's method is another way to think about your differential equation, but this is a numerical method. So what we're going to do is basically make a table. So again, the idea is try to come up with information about the original, even if we could not come up with this solution. So let's say we didn't know what this was. Now, obviously this one, we can come up with this, but there are going to be other differential equations where we cannot solve it. So Euler's method, we're going to do is we're going to basically come up with approximate y values on the original function. And basically what we're doing is just writing the equation of a tangent line. Okay, so we're going to go ahead and start at the point 0, 1, which is given. And I'm going to just go ahead and write the equation of a tangent line. So I'm going to start with my general formula. This is just the equation of a line, right? Okay. Most of the time, you will be given delta x. So that's the change in x, which is really this right here. X minus x1 is your delta x. Your slope is going to come from your differential equation, right? dy dx is really the same as the slope. So at 0, 1, your slope is 0. And then I'm going to plug in my y value. So y minus 1, slope is 0. X minus x1 is delta x, which is 1. So notice I end up with y equals 1 if I move that 1 over. So what this is saying is, if you think about it graphically at the same time, is we have a point on the graph at 0, 1. This is saying, okay, the next point on this graph, you're going to move the x-coordinates up by 1. So I started at 0, so my next x-coordinate is going to be 1. And then your next y-coordinate, we actually calculated using the tangent line. So your next y value is 1. So what this Euler's method does is tells us, okay, the next point on the graph is going to be 1, 1. And basically, I'm just going to repeat this pattern. So I'm going to write the equation of a tangent line at 1, 1. So y minus 1 equals, what's my slope? I'm going to use the differential equation, dy dx equals x, which is 1, and delta x is always 1. And if I solve this for y, notice that you get y equals 2. So the next point is going to be 2, comma, there's your next y, is 2. So this is saying the next point on my graph is 2, comma 2. Okay, I'm going to do this one more time because notice the question is asking me to find f of 3. So the next point, so I'm going to go ahead and write the equation of the tangent line here. Y minus 2 equals, slope here is 2, delta x is 1. And notice here, if I solve this for y, this ends up being 4. So my next point is 3 comma 4. So this is saying the next point on my graph is going to be 3 comma 4, which is up here. So notice you can start seeing that parabola being formed by these points that we're calculating. So f of 3 is approximately 4. This is an approximation using this numerical method. But we came up with the actual solution up here. So if you wanted to know what the actual value of the function at 3 was, we would plug in 3. And if you do this, this is 4.5 plus 1, which is actually 5.5. So the actual value of the function is actually 5.5. Using Euler's method, we came up with an approximation at 4. So that's all Euler's method is. It is an approximation to the y value for problems where we couldn't come up with the solution anyway. Now, the approximation is okay here, but if you want to get a better approximation, what you would do is make this delta x smaller and smaller, so you would get more points to get a tighter fit for that y. Okay, so let's try a couple problems now using Euler's method. Okay, so remember all we're doing is writing the equation of a tangent line. So number 2, they gave us the differential equation. This is the point I'm going to start with. So let's write the equation of the line. Y minus 1 equals, this is your slope, right? So if I plug in 1 for y, my slope in this case would be 2. Notice they tell me that my delta x is 0.25. So x minus x1 is 0.25. And I'm going to go ahead and solve this for y so I can get the next y value. So if you do this, this is 0.5, move the 1 over, so I get y equals 1.5. The next point that I'm going to get to on this graph is your x values will go up by delta x. So this is 0.25, and there's my new y value, 1.5. So write the equation of the tangent line. Y minus 1.5 equals, what's my slope? If I plug in 1.5 here, this is 2.5. And then this is always 0.25. Okay, at this point, it might be easier to work with fractions here. If you have a calculator, you can do the decimals, but if you don't, maybe the fractions would be a little bit easier. It's up to you. If you do this, I believe it's 2.125. So the next point would be 0.5, and then your y value is 2.125. And that's actually what this is asking for, right? The y value at 0.5. So make sure you either circle the final value or tell me this is the value you came up with. And notice I am not using an equal symbol. This is an approximation to the y value. Okay, just trying 2 more. So here's my differential. I'm going to start at the point 0, 4. My tangent line is y minus 4 equals, if I plug in 4 for y, the slope is 2, and my delta x is 0.2. Solve for y. So this is 0.4, move the 4 over, 4.4. My next point, my x goes up by delta x, which is 0.2. My new y value is 4.4. Y minus 4.4 equals slope, ends up being 2.4. And again, you can use the scientific portion of your calculator if you need to. This ends up being 4.88. So then f of 0.4 is approximately 4.88. Okay, let's try one last one. I'm going to start at 1 comma 5. So y minus 5 equals, my slope is 2y plus 1. So if I plug in 5 for y, this ends up being 11. And then delta x is 0.5. So move the 5 over. This is 5.5, so this ends up being 10.5. My next point is 1.5, right? You started at 1. You're going to move the x coordinate up by 0.5. And then my y value is 10.5. So here's my new equation. If I plug in 10.5 here, this ends up being 22 actually. Solve for y, I get 21.5. So the next point would be 2 comma 21.5. So this is the y value that we were looking for.